Thank you. So many thanks to the workshop organizers for the invitation. So I'll be talking about some joint work with Patrick Simonetta Dixmier-Moeglin and Imi Halubchuk. So the framework is it's on simple groups definable in Henselian valued fields. It goes back an embarrassingly long time. It goes back 20 years, really, when Patrick was visiting in Leeds for a year. And we looked at these kinds of questions in the context of ACVF then. And some aspects of the framework of the argument were sort of set up then. But we were more looking at sort of general definable groups, not just simple groups. And we were just in the ACVF context. So now what I'm doing is narrowed just to simple groups, but in a much larger class of valued fields. So the theorem, I'll state from the start. So that K be Henselian non-trivially valued field of characteristic 0. And let's G, so it's just living in the valued field sort, it's just a subset of K to the n, be a definable group. So I'm not making a big deal about what valued field language is, but just a language for valued fields. This is a definable group with finite center Z of G such that G mod Z of G is non-abelian simple. So the conclusion is then that G is definably isomorphic to something which is very much like an algebraic group. So then G is definably isomorphic, so definably isomorphic in K, to a group G dashed, such that there is an algebraic group H, so a semi-simple, almost K-simple, K-isotropic algebraic group H defined over K, and there is some finite central subgroup and Z0 inside the center of R copy G dashed, such that G dashed modulo this center, this central subgroup, is just H of K plus. There's some things that need explaining here. Anyway, but so first of all, it's just a formality, G isomorphic to G dashed. You can think of this as just being G. So what we're saying is that we have this algebraic group H defined over K, semi-simple, almost K-simple. K-isotropic is a condition which somehow makes this HK plus thing non-trivial, or it makes it significant. And then modulo the center, our group is H of K plus. And the groups of this sort will be simple, for example. This is kind of the right group to identify. So I'll say a bit more about what these words mean. First of all, a few remarks. I mean, well, one thing I should say, overall this is work in progress, so there's a slight feeling of a moving object. So I feel faintly tentative about this, but I think it's settled down, and I feel secure enough to state it as a theorem. But not everything is written down. So remarks. So first of all, this is known for k equals qp if you assume G is linear. So it's only known for qp, for k equals qp, assuming linearity. So there's a paper of from 2011 of Raff, Cornulier, Louvain, Casera, and Vallette. So in fact, there's no definability assumption there. They're just assuming the group is topologically almost simple, so no closed normal subgroups once you've thrown away a finite center. But they are assuming the group is inside GLNK. Second comment, it would be nice to weaken this assumption that G mod of the center is simple. It would be nice to weaken that to definably simple. I'm almost sure that's okay. So almost sure we can weaken simple to definably simple in hypothesis. So meaning that there's no proper non-trivial definable normal subgroups. There is a slightly funny issue. We don't actually know that h of k plus itself is definable. So I mean, we know it in standard cases like ACVF, RCVF, QP, but we don't know it in general. So probably the right statement should be definably simple, and then the group here living between h of k plus and h of k. Yeah.
What does equals mean? Like equals, what do you mean by equals?
Right, well, I mean equals, but on the other hand, I mean equals, but in some situations, this group wouldn't be arising. I mean, if h of k plus is not definable, you might not be getting a definable group arising this way.
G prime is an abstract group.
Yeah. G prime just starts life as an abstract group living inside k to the n, group operation. Well, G, yeah. Yeah, so it's conceivable that, that if this thing is not definable, you're not getting examples this way. But in standard cases, QP and so on, you just get you get examples, you get equality. But, sorry? Z0 is finite, yes.
And G prime is definable.
G prime is definable, yes. But I mean, it's just an issue of words, really, I think. It's not really a real issue. Yeah. So the third comment is that this holds also in ACVFP if we assume linearity. So provided we assume linearity, so G mod Z0 inside GLNK. So with
Do you allow infinitely ramified extensions of QP which are not algebraically closed?
oh yes. And then the other comment is this is a bit more tentative. The aim is to prove a version of this with analytic structure as well. So with the kind of analytic structure that stems from the Definably on the p-adics, probably the framework of the Klukas-Lipschitz paper, and we're not quite sure what the final framework should be. So there should be a version allowing analytic structure. under an assumption something like B minimal with centers. So there's this notion of B minimality that Rafa and Francois have, and I think new law argument goes through under that assumption. There's one place where you definitely have to do something different. We know what we want to do, but it hasn't been checked yet. Okay, so I'll say something about the what the words mean. So definitions. So these are some of the words in there. So what does it mean H to be k-isotropic? So H is k-isotropic if it has a split torus, i.e. an algebraic subgroup T definable over K and isomorphic over K to some power of Gm of the objective group. Okay. Then there's this notion of H of K plus, which plays a role. So we're dealing with perfect fields. I'll ignore for the moment the issue of ACVFP there. We're dealing with perfect fields. So we can take H of K plus, so as K is perfect, H of K plus we can take as being defined to be is the subgroup of H of K generated by unipotent elements. So 1 plus nilpotent. And then the other notions, semi-simple, almost K-simple are more standard. So semi-simple just meaning that there's no connected, non-trivial, solvable normal subgroup. And almost K-simple meaning that there's no connected normal subgroup, proper non-trivial normal subgroup defined over K. Okay, so algebraic group defined over K. Okay, so one or two sort of facts around these notions of k-isotropic and HK plus. So these are some classical things, I think. So for H semi-simple and connected, semi-simple connected, that's built in. H is k-isotropic if and only if H of K plus is non-trivial. And then if K is infinite, if the field is infinite, and H is almost K-simple, so the assumptions we have here, so almost K-simple, semi-simple, K-isotropic. So under the assumptions we have up there, then H of K plus is something big. So H of K plus is Zariski dense in H of K. And modulo its center, it's abstractly simple. And H of K plus modulo the center is abstractly simple. So this is work of the 60s by Tietz. Just as an example to keep in mind, an example which is anisotropic, not with a valuation around, but as an abstract group, as a algebraic group. So SO3R is anisotropic. So part of the content of this is this kind of phenomenon doesn't arise for us. And then I wanted to just flag up again this question. Maybe it's not so difficult, but is H of k plus definable? So yeah, Jakob has already worked on that, some results there. There's this sort of Kneser-Tietz problem of when H of k plus is equal to H of k. This is really under an assumption of simple connectedness. The question of when H of k plus equals H of k. When they are equal, then even without simple connectedness, this will be definable. And that's the case in things like Piatowski closed, real closed, algebraic closed. The problem is this is actually given as the group generated by unipotent elements or generated by unipotent radicals of parabolic subgroups. So because it's a definition in terms of generation, it's not completely obvious it's definable. Okay. Okay, so I'll spend the rest of the talk talking around the proof of this. Yeah. Yes.
So HK plus is in H, actually.
Yeah, sure. Yeah, sure. Okay, so proof. So step one, a lot of these steps are fairly standard. First step is to give the group some sort of topological group structure or manifold structure. So we give G a C1 manifold structure. So C1 meaning continuously differentiable in the sense of the valued field, it makes sense. So we want to endow G with a manifold structure so that the group multiplication and inversion are C1 functions. Formally, we've got a sort of working with a slight loose notion of manifold. So we say that G is indefinable bijection with a group G dashed, which is a definable submanifold of k to the n. That's basically the framework. I won't spend time on that. We're using heavily a paper of Roman Wenzel. And this is a development of Arnon's paper from a while ago on groups and minimal theories, I guess goes ultimately to Weil. So the key point is in this kind of, all of these settings, you know that a definable function k to the n to k to the n will be C1 on a large set. So a set whose complement has a lower dimension. That's the basic ingredient. So we just give it a manifold structure. And then step two, and this should also be okay in the analytic situations. So we have a good notion of dimension for definable sets. So in the analytic situations, we would take this as being topological dimension. So the dimension would be the largest D, such that the projection onto D coordinates has non-empty interior. In the algebraic situations of the theorem, so there's no analytic structure, we can take that definition, or we can take algebraic dimension. So you can take topological dimension, or equivalently, you can take the but the dimension of a definable set X is just going to be the transcendence degree of, say, k of x over k, so x in x, but so maximum transcendence degree, but working in a elementary extension, so in a sufficiently saturated elementary extension. So standard notion of dimension. And this would coincide in our situations with topological dimension. And it has nice properties. So the dimension of a finite union will be the maximum of the dimensions. You have a nice additivity property for definable functions. And then a key thing is that from a paper of Lau's from a while ago, that if X is definable non-empty, then X has non-empty interior in its Ricci closure. And this is something where if we work with analytic structure, we have to modify the argument at that point. Okay, so that's a tool available. I'll move this up. So these are just observations. So step 3 is arranging that the group is linear. So sort of linearity. So we arrange that G is inside G and NK after factoring out a finite center if necessary. And this is the step that we can't do in characteristic P. We don't know how to, so we assume that at the start in characteristic P. Again, it's the framework of the argument is standard. So we have this C1 manifold structure on the group. We have a notion of tangent space, and so for G in G, we have the action by conjugation on itself. So we have the map int G from G to G, just given by, say, x goes to G inverse xg. And then you can take the adjoint the adjoint map will just be the differential of this, so dE into G, which will be a map from the tangent space, this all makes sense to itself, and it'll be linear. So it's familiar argument. You can think of this, the adjoint of an element as being a matrix given by a Jacobian fed to a basis. So you can think of it as a matrix. And it gives you a representation. So this gives you, gives a representation, rho from G to GLNK. And of course, then you can ask what the kernel is. This is all definable. If the kernel, say, was a finite center, we'd be very happy. We'd have embedded the G into GLNK modulo center. The kernel is definable. Our group is simple modulo finite center. So the only problem would be if the kernel was the whole of G. So the problem is show the kernel of rho is not equal to G. So So suppose the kernel is G. So what does that mean? It means that so for all G, the adjoint G is just a density map, right? And then with a little argument, I mean, I guess it's a variant in our setting, our sort of definable setting of a standard argument. You get that the tangent space of the centralizer of G is the tangent space of the whole group. So after all, G is acting, so how to say this? So, yeah. Okay, I'll leave that. So we have that. And then hence you get that the centralizer of G is open in G and same dimension as G. Okay. So we get into that situation. So this was a situation that actually really confused me for a while, whether this is a reasonable thing to happen, to have, say, a simple group where all centralizers are open, something like that. And so there's a nice argument that eliminates that. So now, I mean, just because of definability. So for H in G, you just consider the map just phi H, G to G, just the form phi H of X is just the commutator, X inverse H inverse XH. So it's a perfectly good definable map. So now you can check that, so then phi H of X equals phi H of Y, if and only if it's a calculation Y is in the centralizer of X, centralizer of H times X. So the fibers are just cosets of the centralizer of H. Now, okay, that's just a calculation. Now we know the centralizer is open in G, so these cosets are all open in G and of full dimension. So we've got a locally constant map. Phi H is a map from G to itself, which is locally constant. So these fibers are all open. And just by dimension arguments, this forces that the image of phi H is finite, and that G centralized in G of H is finite. But of course G is a simple group, modulo a finite center, so that means the centralizer is the whole of G. So centralized in G of H equals G for all H in G, so G is abelian. And I hope I remember to say at the start, G is not abelian. It's a contradiction. Okay, but I think something is, I mean, it's a very short argument. I think something is going on here. I mean, as I understand it, it's an open question whether you could have a p-adic analytic, say, topologically simple group with trivial adjoint representation. Sorry, so the question is, could you have a p-adic analytic group, topologically simple, so no closed normal subgroups, with trivial adjoint representation? So as in this sort of situation, where you have centralizers all open, and so on. So there's a paper of Capras, Reed, and Willis, which mentioned that as an open question. Okay. Okay, so, so next step. So definition, G inside, say SLNK, doesn't matter, is bounded. If there's just this is a group of matrices, if there's a lower bound in the value group on the valuations of all the matrix entries. So if there exists gamma in gamma, such that for all G written as a matrix Aij in G, the value of Aij is greater than the gamma for all I and j. Okay, so then the proposition is, so let G be a definably almost simple, so I'll phrase it this way, subgroup of SLNK. Then G is not bounded. So here we're kind of ruling out phenomena like SO3R. Maybe just one sort of comment, an obvious example of a bounded group. So an example of a bounded group would be SLN-O, SLN evaluation ring. And you could imagine how this could fail to be true. I mean, if you took a valued field, I don't know, a Hahn field, say Laurent series C of t, something like that, and added in a predicate for C for a pullback of the residue field, so it's a copy of the residue field. So then that copy of C would be definable, and hence SLN of C would be definable inside, and that would be a perfectly good, definable, almost simple group. So it's important that you can't do that kind of thing in our context. So the intuition for the argument here is it's something like a Brouhat-Dietz building argument. So the idea, I mean, for example, if you had SL2, this would act on a tree. The standard action of SL2 acting on a tree, or a tree-like object anyway. You would take an element, a vertex, you would take its orbit under the group. You could argue that because the group is bounded, that orbit is somehow bounded, and it should have some sort of center of mass, some sort of centroid. And the stabilizer of that should be a conjugate of SLN-O. That's the basic idea. So you conjugate yourself into SLN-O, and then SLN-O has this chain of normal subgroups, congruent subgroups of trivial intersection, and that should sort of kill off simplicity. That's the idea of the argument. So I mean, we had some trouble sort of finding the right formalism for it. So I mean, in the end, we were using the way things are used, the approach of Anne Parot. So the first observation, I guess, is that the field K just is definably spherically complete. So we have that. So any definable chain of balls will have non-empty intersection in K. Okay, so now we wanted to get this something like a Brouhat-Dietz buildings argument. So let V, so we have a given n, and we're inside SLN of K. So let V be K to the n. So we want to look at valuations on V. So valuation eta from V to gamma union infinity. What is this? Just the obvious axiom. So you just want that eta of u will be infinity if and only if u is 0 for a vector u. you want that eta of A times U, A is a field element, U in V, should be the value of A plus eta of U. And then you want eta of, say, U plus W is at least the min of eta of U, eta of W. Okay. So notion of valuation. So G acts on the space of all such valuations. So G acts on the space U of all valuations on V. So the action would just be G dot, if eta's valuation, what should G of eta be? Well, G of eta applied to vector U should just be eta of G inverse of U. That's a pretty good action. And then, so this is just stemming from the argument of Bauer, I guess. So we'd say that eta is adapted to a basis, say, f1 to fn of V, if eta of any linear combination of the fi's, so eta of any expression sigma ai fi, is just equal to the obvious min of beta ai plus eta of fi. That's a good notion of it being adapted to a basis. And then there's a lemma which is a kind of definable analog of sort of classical thing, is that if the field is definably spherically complete, and you have a definable valuation, then it's adapted to some basis. So that's cut off the board. So lemma, so if K, the field K is definably spherically complete, as ours is, then every definable valuation on V is adapted to some basis. Yeah, sure.
Do we need to know more or less what is definably spherically complete?
Yeah, so take a definable chain of balls, then the intersection is not empty. Yeah. So now we have our, we're trying to prove that G is not bounded. Okay, I didn't actually say it. We're trying to prove that G is not bounded here. That's the goal. We're trying to show G is not bounded. So suppose G is bounded. So take the standard basis. So let E1 to En be the standard basis of V, and take the corresponding standard valuation. So define E. Yes, V is k to the n. Thank you. Equals k to the n. Okay. Define eta naught just by sigma ai ei is just the min of the values of ai. So this will have stabilizer SLNO. Okay. And then we have our group G, which is bounded, and we want to take the orbit of G and take an average of the orbit of G. So we define eta of x to be the infimum of G dot eta naught of x, where G is in G. And here I'm pushing some details under the carpet. So essentially, we have to justify why this makes sense, taking an infimum there. Essentially, we have to take, in some situations, take a definable coarse length evaluation. There's a little bit involved there. But you'd possibly taking it as a quotient valuation or taking a coarse valuation, this makes sense. So you obtain a valuation, and then you normalize it, and then you take a map from this basis to the corresponding basis for this. So this valuation will be adapted to a basis. You normalize the basis, take this basis to this basis, and then, well, the inverse would conjugate the stabilizer of this into SLNO. So what you obtain is that some G to the H is in SLNO. So essentially you argue that this eta is conjugate to eta naught. Eta naught has stabilizer at SLNO, and hence you obtain this. So then, after that, you can suppose G is inside SLNO. As I said, that has a filtration of normal subgroups, these congruent subgroups, or trivial intersection, and a little bit of argument, you can eliminate that, which can't happen. So we now know that G is unbounded. So I'll finish the argument from there. So this is step 5, conclusion of the proof. It's really this step. I mean, I think everything I've said so far, I think would work with analytic structure. It's the step now which needs to be replaced. So we have our group G, which we know is unbounded inside GLNK. So the Zariski closure of G in K-alg is going to be is the group of, if you like, K-alg rational points of an algebraic group H defined over K. So this H is supposed to be the H of the theorem. And with a little bit of argument, you can check that H is semi-simple, almost K-simple, and connected. So, for example, if H had a normal, proper algebraic subgroup, you could look at its intersection with G. The idea is you could take a normal subgroup with G. That's the idea, and standard arguments. And also, we know that G is valuation open in H of K. So because it's Zariski dense, it has non-empty interior, and hence being a group, it'll be valuation open in H of K. And now we use a couple of results from an old paper of Prasad. So he actually attributes them to others. So there's a paper of Prasad with nice proofs of results. First result he attributes to Bruja, Tietz, and Rousseau. So this would say that it says h of k is bounded if and only if h is anisotropic. And the second, which this is due to Tietz, but I think both cases, Prasad's giving his own proof, says that any proper open subgroup of h of k plus is bounded. Open in the valuation topology here. So it was slightly disturbing that the proof given in this seemed to be working with a valuation with Archimedean value group. So we convinced ourselves we could see how to make it work for an arbitrary valuation. And I also checked with Prasad. He assured us that he knows how to adjust it, both results. The proof for this one doesn't use Archimedean value group, but this one did seem to use, as proved, Archimedean value group. I think it's okay in general. Yeah. Sorry? Yeah, early 80s, yes, 1981 or so. Yeah. Prasad. So the paper is by Prasad. So it's his proofs of these results. Gopal Prasad. Yeah. So what can we do with this? Well, by 1 plus step 4. So as we know G is unbounded, and G is inside h of k, that means that h of k is unbounded, so you get that h is k isotropic. But also you get that, also one can show that h of k plus is valuation open in h of k. We know, I guess it's up there somewhere, that G is valuation open in h of k. So G intersect h of k plus is open in h of k, and so infinite. But of course, h of k plus is normal in h of k, and so this is a normal subgroup of G. So that's, yeah, I didn't know I actually said that, but h of k plus is normal in h of k. So h of k, so G intersect h of k plus is normal in G, which is supposed to be simple apart from the finite center. So you obtain that G is inside h of k plus. That's the only way out. But now we apply the second part here. If this was a proper containment, then G would be bounded, which we know is impossible by step 4. So by step 4, well, by step 4 plus 2, the second result from the Prasad paper, this forces G equals h of k plus. Okay, I'll stop there. Thanks.